Good morning, this is Professor Shannon Gracie. Today we'll be covering inequalities involving quadratic functions. This is section 3.5 from the Sullivan and Sullivan Precalculus with enhanced with graphing utilities text. So let's get started by warming up. We're going to find the zeros of this quadratic function. So pause the movie and get those brain cells moving. Okay, let's see how you did. So to find the zeros of this function, we set the function equal to 0 and solve for x. And you can look at factoring this, or if you're not a fan of factoring, we can use the quadratic formula. So remember that x is the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. So a is 3, b is -1, and c is -5. So we'll have x is equal to the opposite of -1 plus or minus the square root of -1 squared minus 4 times 3 times -5 all over 2 times 3. So moving right along, we'll have 1 plus or minus the square root of 1 plus 60 all over 6. And we'll get x is equal to 1 plus or minus the square root of 61, which is already reduced, all over 6. So you end up with 2 zeros, 1 minus root 61 over 6, and 1 plus root 61 over 6. How'd you do? All right. Well, the good news is that skill there, finding the zeros of a quadratic, is something you've been working on for, a while in your math life. So this skill is something that we'll be using a lot in this section. So here we go. Steps to solve a quadratic inequality. And I'm not sure if we might want to call this 1b and add in maybe a 1a. And for 1a, we would want to get 0 on one side of the inequality. So that'll give us a quadratic function on one side and 0 on the other. So then what you're going to do is you're going to find the zeros of the quadratic function f at x equal to the left side, which would be a x squared plus bx plus c. So then you draw a number line using the zeros. So if there are no zeros, you would test any number in the interval. But if there are zeros, you're going to end up separating the number line into intervals. So if you have 1 0, you'd get 2 intervals. 2 zeros will yield 3 intervals. And then no zeros, no real zeros, will give you 1 big happy interval. So then you choose a number that is not the 0 from each interval and evaluate the number in your function. F at x is ax squared plus bx plus c. If you get a positive result, then that interval is the solution for inequalities with greater than or equal to. If you get a negative result, then your solution would be, then the interval is the solution for less than or equal. Then you write your result in set and interval notation. If you have an or equals to situation, the endpoints are included unless you get infinity or minus infinity as one of the endpoints. Okay, if you have more than one interval that satisfies the inequality, you either use the word or in between the inequalities in set notation or the union symbol to join the intervals in interval notation. All right, so we've got a few examples here. We're going to work this out by hand. This is a very important skill for calculus. You're going to be using this in calculus, but you'll be testing this on you'll be running a similar test on both the first interval to find out if the slope of the graph is positive or negative. And then if you run this test on the second derivative, it'll give you information about the curvature of the graph. But for now, we're just going to figure out if we have positive or negative y values on a given interval. So here we go. We already have 0 on one side of the inequality. So why don't we go ahead and we're going to let f at x equal to the left side, which is x squared plus 3x minus 10. So first step is find the zeros of this. So 0 is equal to x squared plus 3x minus 10. So finding the zeros, this one looks to me like it's going to factor. So we'll have x plus 5 times x minus 2 is equal to 0. So x plus 5 is 0, or x minus 2 is 0. If you did the quadratic, if you wanted to use the quadratic equation, you can do that as well. You'll get your results just fine. So we'll get x is equal to negative 5 or x is equal to 2. So we have just found the zeros of the function. So our second step here, you make yourself a number line. Okay, so this is a number line representing the domain. So we found zeros of negative 5 and 2. So those were actually we'll write them in red. Negative 5 and 2 are the zeros, right? So they're going to divide up our interval into, our number line into 3 intervals. So you'll have potential of minus infinity to minus 5, and then negative 5 to positive 2, and 2 to infinity. That's how we divided up the domain into intervals. So thirdly, you take your original function, which is up there, and you evaluate numbers that are, in the domain, but not the zeros. So here we'll go ahead, let's just use negative 6 for this interval. 0 is usually easy to test, and then 3 is a number in this interval. You could have chosen negative 100 for that left interval. You could have chosen any number between negative 5 and 2 in the middle interval, and you could have chosen, I don't know, 5, 25, 800 for the rightmost interval. I just chose numbers that were in the interval that I thought would be easy to evaluate. So here we go. We're going to just figure out if these results are positive or negative. So when I evaluate our function at negative 6, it'll be negative 6 squared plus 3 times negative 6 minus 10. So this will be 36 minus 18 minus 10. And so f at negative 6 will be positive 8, I believe. Is that right? Yes. So that means that in this interval here, this leftmost interval, every single y value will be positive. Okay, next up, evaluating f at 0. So we'll have 0 squared plus 3 times 0 minus 10. F at 0 is negative 10. So every number in the middle interval, every y value in the middle interval is negative. Okay, and then the last number we were going to test is x equal to 3. So we would get 3 squared plus 3 times 3 minus 10. So f at 3 is 9 plus 9 minus 10. F at 3 is 8. So this 8 is a positive number, so that means we get positive y values for every input value in that interval. All right, so basically we were testing for positiveness or negativeness. I don't even know if those are words. Because we were able to do this because of the fact that we set it up where 0 was on one side. So in Mathese, greater than 0 implies positive. So greater than 0 implies positive. And less than 0 is Mathese for negative. Okay, so the fourth step is, well, what the heck do we do with that result? So our original inequality had a greater than symbol. So we will only take the intervals that yield positive y values. So do you see that the left interval and the right interval yielded positive y values? So those intervals about x are the answers. So let's see, we had minus infinity to minus 5 was a positive, and then 2 to infinity was also a positive. So that's what we put for our answer. So our answer will be, so in set notation, you would say x such that x is, now it's only a greater than, not a greater than or equal to. So x is less than negative 5, because minus infinity to minus 5 means x is to the left of negative 5, or x is good, greater than 2. Now in the interval notation, which by the way is much more commonly used, so you need to learn the interval notation, we would have minus infinity to minus 5. The parentheses means we're not including the endpoints. Union 2 to infinity. And that's your answer. So graphically, it's really kind of cool. If we break out the graphing calculator, and we'll get up to what our original inequality was. So here with the graphing calculator, clear these out, we would have x squared plus 3 times x minus 10. So a couple ways we can do this. You can just do the regular graph. I think we're going to have to adjust our zoom a bit. I'll try zoom standard. So let's zoom, let's look at our window. Let's do our y minimum lower. Let's call that negative 15 and see if we get there. There we go. Okay, so do you see what we were doing here is we were testing to see where we had positive or negative outputs on here. So if we just verify this graphically, so this is what was going on. So I think this is what, 10, negative 15, and then this was 10 and negative 10. Actually, this is this tick mark. This is x, and this is f at x. So what we found is that the y values, so if I highlight the y values in yellow, we had a greater than situation with our inequality. And so do you see our y values are greater than 0 on those intervals? Well, the corresponding intervals on your x are here to here. Isn't that kind of groovy? So that's what we found. Right here, we had found that this 0 was the, -5, right? So this was -5, 0. This here was the ordered pair 2, 0. So those are ordered pairs. And so the whole interval here, this whole interval here, was the interval on x where x goes from 2 all the way to infinity. And this interval here was x going from minus infinity to -5. So these here are ordered pairs, which represent the x-intercepts. And then these guys here are all solutions to f at x greater than 0, which was x squared plus 3x minus 10 greater than 0. Whoa. Okay? So pretty cool stuff there. And I'm going to say interval of all solutions to that inequality. Intervals. Okay, so there we go. So it's up to you. I mean, we're doing the same kind of stuff for each of these problems. So if you feel very confident, go ahead and work them through yourself. Don't just use your graphing calculator first, okay? You need to you need to solve them by hand and verify your results using the graphing calculator. So if you feel confident, pause the movie, do the last 2 problems. Otherwise, just follow along with me. All right, are you ready? Awesome. Let's go. So for this problem, do you see that I need to work a little with this inequality, right? Because I don't have all these terms on one side. So basically, if I subtract if I subtract 6 and if I subtract 5x from both sides, and then on the left side, I'm going to be writing these in descending order. So I'll have 6x squared minus 5x minus 6 is less than or equal to 0. Now I've got it set up. So I would let, f at x equal to 6x squared minus 5x minus 6. So our first step was, find the zeros once we've gotten 0 on one side of the inequality. So 0 is 6x squared minus 5x minus 6. I'm just going to use the quadratic formula on this one. So x is the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we will have x is equal to 5 plus or minus the square root of. So that'll give us 25 plus 144 all over 12. So now we will have x is equal to 5 plus or minus the square root of 169 over 12. 169 is a perfect square. 13 squared is 169, so we get 5 plus or minus 13 all over 12. So x is equal to 5 minus 13 over 12, or x is equal to 5 plus 13 all over 12. So here we would get x is negative 8 twelfths. So x would be negative 2 thirds. This here would give us x is 18 twelfths. So x would be 3 halves. So those are the zeros. Okay, so our second step is make our number line separated by our zeros. So we've got the zeros were negative 2 thirds, remember those are the x-intercepts, and 3 halves. This makes up the following intervals. So we'll have minus infinity to minus 2 thirds. This will be minus 2 thirds to 3 halves, and this will be 3 halves to infinity. Okay, I'm going to rewrite our function down since it's hiding. So the function we're testing in is f at x is equal to 6x squared minus 5x minus 6. So let's pick numbers to test. Let's see, negative 1 is to the left of negative 2 thirds. 0 is in this interval, and positive 2 is to the right of 3 halves, so those numbers will work. So then we'll be evaluating f at negative 1 is equal to 6 times negative 1 squared minus 5 times negative 1 minus 6. F at negative 1 is 6 times 1 is 6 plus 5 minus 6. So f at negative 1 is 5, and 5 is greater than 0. So put a little positive sign in there. Now, I'll just do it over here. F at 0 is 6 times 0 squared minus 5 times 0 minus 6. So f at 0, do you see, will be negative 6, which is less than 0. So we'll put a minus sign here. And then lastly, f at 2 is 6 times 2 squared minus 5 times 2 minus 6. So f at 2 is 24 minus 10 minus 6. So f at 2 is 8, which is greater than 0. So we'll put a plus sign there. Now let's look at what our original, our modified inequality said. So we're looking at this here, this inequality right here. So when we look at this inequality, it said less than or equal to. So we're looking for the intervals that got a minus in there, which was the middle interval, and we're going to, include the endpoints. So this was our third step, and our fourth step is our conclusion. So what we found was x such that, negative 2 thirds is less than or equal to x, which is less than or equal to 3 halves. So all the numbers in that interval will yield negative y values. And so writing that in interval notation, we use the brackets. The brackets tell us that we're including the endpoints. And that's the answer. Okay? So again, coming over here and putting in our function, this one is, 6 times x squared minus 5 times x minus 6. Graph. And actually, let's just zoom standard and see what that looks like. Okay, so this guy what we'll have going on is our scale, again, is that's x and f at x. And so our inequality, we were interested in negative results. So those are all the y values we were interested in. Now the corresponding interval on x is this guy here, that interval. So our zeros were here and here. That was I'm just going to write it as x is equal to negative 2/3. This here, x is equal to 3/2. And this interval right here is the interval we found, negative 2/3 to 3/2. Okay? So again, I want to get this in standard form. So I'm going to work with this inequality. If I distribute the 2 through, I'll get 4x squared minus 6x is greater than negative 9. And if I add 9 to both sides, I will have 4x squared minus 6x plus 9 is greater than 0. So we're going to let f at x equal to 4x squared minus 6x plus 9. So first step, find the zeros. So 0 equal to 4x squared minus 6x plus 9. I'm going to use the quadratic formula again. So x is equal to the opposite of negative 6 plus or minus the square root of negative 6 squared minus 4 times 9 all over 2 times 4. So x will be positive 6 plus or minus the square root of 36 minus 144 all over 8. So we will get x is equal to 6 plus or minus the square root of negative 108 all over 8. We have a negative under the radical, so this means that there are no real solutions. Remember, you would get an imaginary solutions for that. And we're looking for the x-intercepts so we can figure out this inequality. So that's okay, don't panic. What you do, you still make your number line, but you know what? It goes from minus infinity to infinity, so you don't break it up at all. So you just pick a test value. So why don't we pick 0, right? So we only have to test one number this time, and that number we just picked as 0. So f at 0 is, so what was our original function? It was the 4x squared, so f at x is 4x squared minus 6x plus 9. So f at 0 is 4 times 0 squared minus 6 times 0 plus 9. F at 0 is 9, which is greater than 0. So the whole interval goes from minus infinity to infinity, and it has positive y values. So let's take a look at our inequality. that we found. So this is the inequality once we got 0 on one side. We are looking for greater than 0 solutions. So we end up getting all real numbers work as solutions. If we had gotten a negative there would have been no solution, but we got a positive and we had a greater than. So therefore, our solutions, so this was part 3. So part 4, the solutions, x such that x is a real number, or minus infinity to infinity in interval notation. All right, so let's take a look at this graph. So this one is 4 times x squared minus 6x plus 9. So if we graph this one, all right, so let's adjust our window. We need higher y values. So we'll have something like this. So let's, as you notice, this one is above the x-axis. It's never going to cross the x-axis, which is why we got complex solutions instead of real solutions. So if you take a look at the graph, do you see all y values are going to be positive? So we will have this situation. And this is our f at x, and this is x. So all of these y values are positive. So the whole real line is going to be the solutions. Isn't that cool? All right, so believe it or not, that wraps it up for this lesson here. So I hope you have a fabulous day, and I'll be talking to you soon. Bye.